We will go ahead and get started looking at our Aldol reactions in a little more detail than what we saw in lab. Not by much, though. So we've got the overall mechanism shown up here. One of the things that it's important to kind of note when you look at your aldols is sometimes you may see a tip-off that you're looking at an aldol reaction, sometimes not. It really just kind of depends. So as an overall reaction, you might see something along these lines. Hydrogen, and then say the reagent, what are we going to use? Let's go ahead and use hydroxide. So it could get written like that on the test. Okay? And what they're expecting you to do is draw this as your product, okay? Which seems a bit kind of mean. Okay? Because when you look at that equation, you don't see two carbonyls, or you don't see really two oxygens, and you definitely don't see all those carbons that show up in the product. So it becomes, why are they going through and doing that? Because I guess for some reason they feel that if they put a 2 out in front, it gives it away. So they decided not to include it. Okay? So be kind of aware of that. The next issue that we could go through and address with this is if we then changed up our base, let's say instead of using hydroxide, we used LDA. Any ideas what you might expect the answer to be in this case? Would you expect the same circled product? No, why not? Pulls off the exact same hydrogen. No. LDA is a stronger base, so it irreversibly removes the hydrogen. And so the LDA goes through and reacts and completely removes that hydrogen, and what we would expect in the presence of LDA is our nucleophile, okay, as our primary product. Okay? So be kind of aware that you might see a base issue pop up with these. Okay, and we'll come back to using LDA versus a strong base in a couple other cases. But if we're trying to run the aldol, more than likely what they're going to give you, particularly if it's a self-aldol, so we're reacting the same two aldehydes, we're not going to use a ridiculously strong base. We're going to use something that's a little bit more mild. We could use something like hydroxide or an alkoxide species. As soon as we see that LDA, really what we're pushing there is to take it directly to the nucleophile. We don't get any kind of addition reactions.
So it wouldn't go back to the original?
It wouldn't go back to the original, and the reason why has to do with our pKa's. Okay, the pKa of our aldehyde is substantially lower than the pKa of the conjugate acid of LDA. Okay. So we see that as a unidirectional thing. And we talked about LDA versus other bases in that issue, and that's one of the things that you have to be aware of. Okay? So our very first step is going to be to remove that hydrogen. So we're doing what the textbook likes to call a proton transfer. I would like to refer to that as an acid-base reaction. We then go through and have that nucleophile go through and attack our electrophile, which just happens to be a carbonyl. Okay? Just like we saw in the previous chapter, chapter 20, except now our nucleophile also happens to have come from a carbonyl-containing compound. Okay? Once that's occurred, we form our intermediate. Yeah, go ahead and draw that in right there. We've got our intermediate. It has the negative charge on the oxygen. Would we expect, which way would we expect the equilibrium to favor in that step of the reaction? It was a lot further away than I thought. Okay, would we expect reactants favored, or sorry, products favored, or reactants?
Products.
Why would you expect the products favored in that step?
Negative oxygen versus negative.
Yeah, look at the most unstable thing. We're looking at a negative oxygen versus a negative carbon. Negative can be better held on that oxygen, so that would suggest that we would probably see a slight favoring for our product. Okay, looking at the stability of those. At that point, we now kind of stall out. We have that negative oxygen, which is more stable than all of our other previous species, and we're kind of dead in the water. Okay? Usually it's followed up with water, or water's said to be present in the solution. You'll notice here that they just kind of say it's present, even though it's not directly mentioned that it's present. That could very well be as part of the workup, or quenching the reaction. Okay? So we add the water and we protonate and we end up with our final product. This was originally discovered using aldehydes as starting materials. Any ideas why aldehydes would have been used instead of ketones? Your aldehyde is much more reactive. So they saw this product form in standard aldehyde solutions, whereas in the ketone solutions, it doesn't allow for this equilibrium to occur as readily, so we don't see it happen all on its own. Okay? So because our aldehyde solutions were the first ones to do it, they looked at the product and they evaluated and said, hey, I've got an aldehyde and I've got an alcohol, call it an aldol. Okay? And that's the origin, or at least that's my story, as to the origin of what's happening with these, okay, and where they came from. It doesn't have to be an aldehyde. We could also do it with ketones. We can do it with different aldehydes. We can do it with different ketones. Ultimately, they're all Aldol reactions. We're just changing slightly the dynamics of it. And because of that, we see slightly different results. Okay? We can also go through and, well, actually, we just talked about this. We would expect it to favor the products. One of the reasons we would expect it to favor the products is looking back at those intermediates. One of our intermediates, right before we finish the reaction, is putting our negative charge. Oh, geez. Now I got to try and draw this. I'm going to cheat. Use the answers. We've got that negative charge on an oxygen as opposed to the carbon from our enolate. Okay. So in most cases, we do predict to see the forward direction of our product, or a larger percentage of our product in that solution. Okay. And it's all because of that intermediate with that negatively charged oxygen as opposed to the negatively charged carbon. Yeah?
Can the sodium hydroxide and the water be added at the same time? Or is the
Yes.
Why?
And it's almost always going to be added at the same time. Okay, why would they almost always be added at the same time? What phase is sodium hydroxide? It's a solid. Okay, we would very, very rarely ever run a reaction where we have a liquid and a solid. Why? The only place that they can interact is at the interface of that. So typically what we do is dissolve it in some solvent and then do the reaction in the solvent. That opens up more surface area, more potential for reactions. Okay, effectively increases the concentration. Okay, so water is definitely going to get added at the same time. Okay, if we switched it up, let's see, did it actually do it? Yes. If we looked at a ketone as a functional group, we still have that same alpha carbon with that same alpha hydrogen. We could go through, remove our hydrogen. We can generate our enolate. That enolate can go through and attack another one of our ketones. Okay. And after a sequence of steps, we can go through and make our final product. Okay. Why do we not see the same favoring of our product in this case? In this case, you notice that we see much more, or a much larger percentage of our starting material. What's the difference? It's just as symmetrical as if we'd used the aldehyde. Well, I can actually see where you're going with that. It is a little bit more symmetrical with the ketone than it is with the aldehyde. But no.
Oh, so you're not comparing, okay, never mind. I thought you were comparing to the previous reaction.
It is to the previous reaction, yeah. And this one is symmetrical, whereas the last one wasn't symmetrical, okay, with our starting materials. But even if it was an unsymmetrical ketone, we're going to see the same result.
The carbonyl carbon isn't as electron.
Yeah. If we take a look at our primary attack, our electrophilic carbon, tasking. You guys didn't see anything weird on the screen, did you? Oh, that was really weird. Our electrophilic carbon is not as electrophilic in the ketone as it is in the aldehyde. Why? We're looking at two carbons versus a carbon and a hydrogen. Right? The hydrogen doesn't have as much electron density to stabilize our carbon, or sorry, our carbonyl carbon, our electrophile. Okay? Which means the aldehyde becomes much more reactive, which means our electrophile is more electrophilic in the case of the aldehyde, less so as far as the ketone goes. Okay? So when we're looking at ketones, we don't typically expect to see the formation of this product. Okay? Should we take a look at the reverse mechanism, or you guys think you can get that? So yes or no?
Yes.
There we go. So if we're going to try and do the reverse, what's going to happen? We'll take the lone pairs on our oxygen. We'll push those down, okay, to reform our carbonyl. Problem with that is now our carbon has too many bonds. What bond do we break? Okay, we've got three options. We'll call them our red options or our purple option. Why purple? Maybe you're seeing something I don't, so let me go through and take a look at that. So this would be our purple option. Our red option, okay, I accept the resonance argument for sure. Our red option, oh my gosh, I shouldn't have agreed with that. It's going to be ugly. 2, 3, 4, 5. Right? Our red option would be there. Which of those two products is more stable? Why the purple? Actually, if it's an anion, we'd predict the primary to be more stable. There's resonance stabilization through a process known as our ketoenol tautomerization. Okay, which is pretty much everything that drives this chapter. All of the reactions you will do start with a ketoenol tautomerization. Okay, we convert our ketone over into the enolate. Okay, that resonance stabilization stabilizes that intermediate, and so what we end up seeing is our purple bond breaking off. If we want to actually push that all the way back to our starting materials, we can have the lone pair come back down, and this picks up a hydrogen from water in the solution, and we end up right back where we started. Okay. And then that other species would be here. Remember how I was saying they might not give you that 2 in front to go through and do this reaction? We absolutely needed 2 of those cyclohexanones to run that reaction. Okay, which means when we run the reverse, we expect to see 2 produced. There's one there, there was the one there. Okay? Kind of makes sense? So with these, generate the ketone, or generate your nucleophile, and then have it attack your carbonyl, your electrophile. Okay, so all of our Aldol reactions are looking at a carbonyl electrophile. Okay? And we did already allude to this. Why do we see that preference for the aldol product as opposed to the ketone? When we shift to a ketone, we don't see the ketone product. Okay. It has to do with our intermediates. We lose the intermediate in our ketone. Or sorry, we don't lose the intermediate. Our ketone is less electrophilic. Okay. And there's actually one more reason that we could go through and address that's going to become more important later on. Where's the attack carbon? Where is the carbon that our attack occurred at? Okay, versus there. We see a steric hindrance argument as well. Sorry, I thought there was something else showing up there, but I didn't see it. Okay, so we don't expect our ketones to really generate the aldol product. Okay, That said, what could we potentially do with this? Okay. In both of these cases, do we still have an acidic hydrogen? So look at that alpha position. Do we still have a hydrogen in both positions or both cases? Yeah. Which means we have the potential for removing that hydrogen and making that carbon negative. Is there a positive carbon nearby? Say that was maybe even flagged red. Why is that red carbon positive? The electronegativity of the oxygen attached. What happens if I take the electrons and I move them in to make a pi bond? How many bonds does our red carbon have? Too many bonds. So what happens? We break a bond. We can kick out OH. Uh-oh, what's the problem with kicking out OH? It's a horrible leaving group. But what is it leaving into? A lot more OH. Okay? So while in general that is a very bad leaving group, it's leaving into a solution that is already equally unstable. Okay? So yes, it may be an unfavorable situation. What is it? Jumping out of the turkey fryer into the oven or something like that? Okay? Both cases you're going to get burned, but at least you're in a different spot. Okay? So we can see that reaction tend to occur. What type of reaction occurred on that last step? It's an elimination reaction. What molecule was eliminated? Water. What other name do we give to a reaction that's an elimination that eliminates water? Oh, good call. Not the one I was thinking of, but yes, that's right. Dehydration. Condensation is the other one. Okay. What we've just evaluated or looked at is what is known as the Aldol condensation. We run the Aldol reaction followed by an elimination, which gives us our condensation product. So what we get is an Aldol condensation reaction. Okay. This reaction can be catalyzed under acidic or basic conditions. It almost always requires heat. Why? It's an elimination. Most elimination reactions require heat. Okay, again, why do they typically require heat? What kind of bond are we breaking? Between what two atoms? What's the important bond that we really have to break? But you're right, the carbon-oxygen one has to break too. We have to break the carbon-oxygen, but that's polar already. Oxygen's already taken those electrons. The carbon-hydrogen bond is an incredibly difficult bond to break because the electronegativity between those two is very, very similar. So when we run an elimination reaction, we typically need heat to help alleviate and weaken that bond so that we can break it off. Okay? We could use the heat as another argument for breaking off that hydroxide as well. That is a carbon-oxygen bond. Yes, it is polar, but is that leaving group good? No. So if we add enough heat, hopefully we can weaken the bond enough that we can get it to pop off so we can get our elimination to occur as well. Okay? This reaction can be run under acidic or basic conditions, as it says, but why do we most typically see it under basic conditions? No, if we made it under acidic conditions, we could actually have the OH converted into water, and then it's a really good leaving group. We would expect that to be awesome. We very, very rarely ever see the aldol condensation with acid.
Didn't you say something earlier about like hydroxide can leave in a basic condition?
It can leave, but it's still a bad leaving group. So with that logic, why wouldn't we run under the acid conditions where we get a good leaving group? Almost always you'll see it as a base. Why do we always see it as a basic conditions? To do this step of the reaction, what do we have to have? It's not a nucleophile, we need a base. So we need OH minus, we need our either acid or base catalyst, but then what else do we need? We need our substrate, our starting material. How did we make the starting material? By adding a base. To get the aldol, we had to add base. Okay? Why do we typically see the condensation happen under basic conditions? Because to make the aldol, I needed a base to begin with. All I now have to do is add a little bit of heat, and I can push across the aldol condensation and just push it that one extra little step. Okay? We very rarely see the acid-catalyzed aldol condensation. Take it a step further. Why do we typically need a base? Whoa. Oh, no, that did actually work. If we go through and take a look at our ketones, okay, to get this reaction to occur really at all, we need a base. Okay? If we now heat, we can go ahead and break that further off. Under acid conditions, we don't see as much of that favoring. And it's only 20% favored. If we drop it to acid conditions, we're looking at maybe 10%. Okay? If we wanted to do the condensation with a ketone, we have to first make that aldol product. The way we make that aldol product is with basic conditions. If we then tried to acidify it, what happens? The aldol product immediately goes back to the ketone, and now we don't have it to do the condensation. Okay? So when we're looking at our aldol reactions, almost exclusively, they're going to be under basic conditions. Okay? And by almost, I don't think you've seen a single example in either the homework or the ACS test or anywhere else where it's under acidic conditions. Okay? To do the aldol reaction and our aldol condensations, you will see it under base conditions. Okay? Why is it called a condensation?
Loss of water.
We lost that water molecule. Okay? It is still in equilibrium. There are some things that we can do to help prevent that reverse reaction. What ideas do you think you got? We could try and get rid of the water. Okay? If we perhaps distill or use molecular sieves to pull water out of the reaction, we could try and prevent the reverse reaction as well. Is there something else that might help us favor the product? We could try and tweak the temperature, okay, but I would argue there's something even more interesting within this structure. What can you tell me about that pi bond? Everybody's favorite 9-letter word. There's resonance. We've conjugated the double bonds. What happens to our energy if we have a conjugated pi system? Goes down. The stability goes up, okay, but our energy goes down. Pi bonds are higher in energy, but we've conjugated it with the other pi bond. So instead of having 2 pi bonds in distinct locations, I've now spread it over 3 possible locations. So the overall energy is lower. Okay? So we can see that that elimination could actually be favored fairly well in this case. And that typically when you go through and run your aldol reactions, almost exclusively you'll see them as condensations. Okay? The sapling assignment will push you into doing just the aldol result without doing the condensation. I think the only flag that you're going to see for that is no heat. Okay? So that heat is a big kind of a sticker saying, yes, we're doing the condensation. Without that heat, you will probably not see it go all the way to the condensation product. You'll have to stop it at the aldol. Okay? Questions about that? Okay. When we eliminate, wait a second. Oh yeah, when we eliminate water, we do get the possibility for 2 products. What's the difference between these 2 products? Cis versus trans. Which one of them is trans, left or right? Left is our trans, right is our cis. So we're still getting the exact same kind of transfer of electrons between us, just a question of which double bond or how the double bond forms. Okay? Typically to decide between trans versus cis, what do you need to evaluate? Could do stability, but that's not always going to win out for us. To decide between cis and trans, the first thing you have to evaluate is the mechanism. Okay? From the mechanism, you can then evaluate stability. Okay? In the course of running your Aldol condensations, we don't get anything to force the geometry in the cis position. Okay? Which means it's going to go trans. Okay? So you will see primarily the trans product in your Aldol condensations. Almost guaranteed sapling is going to hit you on that if you draw it cis by accident. Okay? And they might even orient the molecule such that it looks like cis is the easiest to draw. Make sure that you set it up trans, because those are going to be your products. Okay? And it has to do with lower energy there. All right? Anything else I want to add on that? Okay, so we talked about all of those. As a general kind of tip to help you kind of see things as far as what happened, if we were going to do the reverse of this, what I would go through and do is cleave your pi bond, and what we'll do is spread those atoms away from each other. Not easy for me to go through and draw. Let's draw that really big double bond. Okay, so I'm going to stretch those apart and now erase it. Okay, on one side I'll put in my oxygen, which should be the opposite side, and the other side needs to be my nucleophilic carbon, which ultimately came from, eraser. Came from our aldehyde. There's our starting material. Okay. So you can identify that double bond, kind of cut it in half. The side closest to the existing carbonyl, make it a carbon. The side furthest from the carbonyl, get an oxygen in there, okay, on your double bond. And you now have your starting materials. Okay, just as a kind of tip to help you sort of see that. Okay? Questions about that? Okay. So actually, we're not quite there. The next thing that sapling, or even your textbook, goes through and does is address it now is a crossed aldol reaction. So instead of taking the same aldehyde or the same ketone and reacting it with another one of itself, we can go through and react two different ones. Okay, so you'll notice we have two different aldehydes. In this case, that means I have two different alpha hydrogens. I have an alpha hydrogen there, and I have an alpha hydrogen here, which means I now have two nucleophiles, and I have two electrophiles. These can now go through and react any number of ways to generate four possible products. So if we're going to try and do an aldol reaction or an aldol condensation or any one of those, we want to make sure that when we combine these things, that we limit the number of possible products. Okay? If we've got four possible products, that's an awful technique. Even if we do isolate the one we want, and say we want this one right here. Cool, I can now isolate that. Great, I've got it. What's my yield? Okay. At best, we're looking at somewhere probably 0.25%. That is an awful yield for an experiment. You effectively threw away 75% of your money, okay, to run that experiment. If that's what you've got to do, then you got to do it, but we want to try and come up with ways to avoid that issue. Okay? How could we go through and avoid that issue? What's that?
Find a different way to put them together.
Along those lines. We can go through and say, instead of reacting these two species where we have both of them have alpha hydrogens, we can go through and pick an aldehyde that does not have an alpha hydrogen. Well, if it doesn't have an alpha hydrogen, it can't possibly act as a nucleophile. It will only act as the electrophile. So what we would end up doing is choosing our reagents very, very carefully such that we don't have this massive amount of products show up as an issue. Okay? So one of our options is that we can remove alpha hydrogens. Okay? The other option is we can go through and make one of them extremely unhindered, okay? Which means it could act even better as an electrophile. So in this case, they chose formaldehyde. There's no alpha hydrogens there, which means, what is that other one? Propylaldehyde will act as our nucleophile with no other options. This has to be our nucleophile, which means when we run the attack, it has to attack, and we end up with one possible product. Okay? The other option is, instead of going something as simple as formaldehyde, because then we don't add any extra carbons, is that when we put on our structure, one of our aldehydes, we eliminate the option of alpha hydrogens. How many alpha hydrogens are on our red benzaldehyde structure? Take a look at our alpha position. How many bonds are shown? 4. There are no hydrogens there. Okay? Without that alpha hydrogen, it can only act as the electrophile, which means we only get, well, not officially only get, we only get this acting as our nucleophile. It's going to be the one that's going to attack. Okay? Why the pseudo backtrack in that statement? Can our nucleophile... Yeah, the nucleophile could still act as an electrophile. We still do have that electrophilic carbon there. Okay? But we would go through and try and evaluate the possible reactivity. This one is absolutely positive, our electrophile. There is nothing to stabilize it. If we go through and look at our nucleophile with those alpha hydrogens, those could potentially stabilize and reduce the reactivity of the nucleophile. At worst case, we'd be getting a 50% yield. More than likely, we're pushing even higher than that. Okay? So that's one way that we could go through and avoid it. But like we said already, that does cause an issue still, because we still have that electrophile ability. Okay? The last thing that we could go through and do is, instead of mixing everything in one big pot where now a whole bunch of different things can happen, we decide to break apart those individual chemistries. Okay? To make our nucleophile, what do we need? We need our alpha hydrogen structure, which is this guy, and base. So let's do that reaction first. But remember, we don't want it to act as an electrophile. So we need to make sure that that reaction is not reversible. How can I do that? Use a stronger base. Instead of reacting with sodium hydroxide in one pot, we could switch to a new situation where what we decide to do instead is take our aldehyde, react it with LDA to completely push across to our nucleophilic structure, our nucleophilic enolate. Now I can mix it with the one that I want to act as an electrophile. Okay? So I'm trying to control when those individual reactions occur such that I can maximize the amount of product that comes out of it. Okay? Kind of makes sense? Okay. So those are your two options when looking at crossed Aldol reactions as far as deciding what reagents you should go through and use. Try and piece them together as carefully as you can to make sure that you get the best combination possible. Okay, so the crossed ones, you just have to be a little bit more careful about how you approach them to make sure that you get your optimal situation. Okay, so it's going to be a reagent mixing, effectively, is your issue. Last issue that we could go through and see, everybody's favorite, including the ACS test, intramolecular reactions. Okay, so what we're saying is a single molecule has both an electrophile and a nucleophile, and it can react back on itself. So that when we go through and take a look at the compound shown here, do we have alpha hydrogens? Yeah, we got lots of alpha hydrogens. Got here, here, in fact, here and here. So pretty much any one of those positions could act as an alpha hydrogen. If we go through and run that equilibrium reaction, we could generate, since those are effectively equivalent, a negative charge here or a negative charge here. Okay, to stabilize those in a condensation or an Aldol reaction, what do we need? What do you react with all negatives? Positive. Where do we have positively charged atoms? On our carbonyls. Which of those two carbonyls is the most likely to react? Left or right? The right, because true. Our left is already really, really close to our nucleophiles, but there's something else going on with it that makes it less electrophilic.
The ring strength?
Resonance. It is already being involved. It's already acting as an electrophile, but only one bond away. So effectively, it's resonance. Those negative charges can come in and stabilize that positive already. But it's a temporary thing. We can't permanently stabilize it in that case. So what happens? We're looking at those negatives reacting with our positive. Okay? 2 negatives, 1 positive. That means 2 possible options. Let's see what happens. We take 1 negative to our positive. How many atoms would be in that structure?
3.
We got 1, 2, 3. Okay? We're not changing the connectivity of the carbons around our electrophilic carbon. All we're doing is connecting those, which means we now have what size ring? A 3-carbon ring. Okay, so this is how I would approach it. I draw my 3 carbons, and now I'd say I am way too confused to be able to see this clearly, so I'm going to go back through and number. Carbon 1, carbon 2, carbon 3. Now I'm going to go back to my product and say here's carbon 1, 2, and 3. What things are attached to carbon 1? We have a negative oxygen, and a methyl, and officially, though it's already drawn, no, we don't have a hydrogen. Carbon 2. Then we can move to carbon 3. Nothing special there. Or sorry, there is something special there. What's bound to carbon 3? Okay, see the pieces? The intramolecular, extremely difficult or easy to lose carbons. Draw them out as carefully as possible. Okay? Absolute worst case, make it incredibly ugly, and instead of drawing that 3-membered ring, okay, though I don't particularly like it when you do this, but you can do it. Okay, yes, I will perfectly accept that for a short answer. Okay. Yes, you have an incredibly ugly bond, and there was a shorter distance that you could have gone to connect those two. Okay? But it is perfectly valid. What you're trying to do is show that you've connected those atoms to each other. Okay? With the propane, it's not too bad. It's just a single connection. And if we compare those 2 structures, they're now matched up. Okay? So that was one option. Which, any guesses? Was that the correct answer? Probably not, considering not the answer that was drawn. If we take a look at our other option, we're going to have the other nucleophile attack. And we would go through and evaluate our carbons again. Okay. What makes this even more tricky in this case is what else did they add? Heat, which means it wasn't just the aldol, they also did the condensation on top of it. Okay. Where is carbon number 1 in our product? Or said another way, is there a carbonyl that was not touched in our reactant? Number 4. There's no arrows around number 4. Okay. Do we see a carbonyl in our product? Yes. That carbonyl carbon should be carbon number 4. Nothing happened to it. Now we got to decide which way is which. In the condensation, what do we form? Condensation is an elimination. We form the double bond. That double bond needs to be forming between which 2 carbons? 1 and 5, which means when I see this double bond, that is either carbon number 1 or 5. Which one should it be? 5. Why?
5's a lot closer to 4 than 1.
There you go. 5, which means our next carbon is 1, 2, 3. Where was our oxygen eliminated from? Carbon number 1. Okay? The intramolecular reactions are incredibly difficult because everything's happening on top of itself. It's very easy to lose track of each of those individual pieces. Number. If you number your atoms, you should be able to find those pieces a little bit more quickly and hopefully be able to do those intramolecular reactions efficiently. It will still take time, but you'll at least get it right. Okay? So between these two possible products, which one do we expect? Orange or purple? Or, yeah, I guess that works. We expect the orange one, why? Angle strain. If we take a look at our purple structure, that's a cyclopropane. We have to really crunch down on those angles. Really, to get those propane structures, we have to have very special conditions to force that ring to form. We definitely don't have those special conditions. The one that is more likely to form is our 5-membered ring because we have less angle strain to get those two atoms to interact with each other, atoms 5 and 1.
Could we see the special conditions on the ACL?
They wouldn't be an aldol reaction. You could look up cyclopropane forming reactions, and yes, you could potentially see those. The common one is a carbene. We can talk about that after exam 3. Okay? So typically when we're looking at our intramolecular aldols, we're looking at 5 and 6-membered rings forming because they have the lowest angle strain. Okay? Questions about our aldols? Okay. Actually, it's a little bit of practice here. So which aldol method was done in this case, in each of these? Yeah. So that first one is what? It's an aldol condensation. Next one, I guess left to right. So what product is this? It's an aldol product that came from, you're right, ketones. Last one, condensation. What are you looking for to identify that it was a condensation? Is it just the double bond? You're looking for a double bond at the alpha position to a carbonyl. Okay, so it's all of that you're identifying for your aldol condensations. You need all of those pieces. If we wanted to do the reverse reaction and figure out where these pieces came from, okay, stretch your double bond, okay, in that first case, and we'd end up with, so we stretched it out, that atom is a carbon, so that would be our carbon nucleophile that attacked. Our electrophilic carbon. Okay, and there's a ring in there. Sorry for the mismatch on colors. Self-aldol, cross-aldol. Self-aldol, if we go through and count our carbons, there's 1, 2, with our 6, we got 8. 1, 2, and there's our 6, we got 8. Okay. Not always the easiest thing to see. Remember, your structures can flip, spin, and rotate. Okay? Does that give you enough of an idea with those? Okay. We will go ahead and move on then. Instead of looking at aldehydes and ketones, is there another place that we could see carbonyls? Esters. We typically won't see it with acids. Why not with acids? Carboxylic acids? We still have that keto resonance. It's just not as strong. Why is it not as strong? The carboxylic acid is acidic, so we get that acid kicking off. Really what we're looking at is the carbonyl carbon being partially positive. With the acid functional group, you now have 2 oxygens that can share electrons very readily in between. Whereas with the ester, we can't lose that hydrogen because the group that's attached is not a carbon or not a hydrogen, it's a carbon. Okay? So we see a little bit less stabilization of that positive, so we can see Claisen or the ester functional group go through and do these condensation reactions or these aldol equivalent condensations. Nothing about the chemistry changes. We still form the enolate. The the enolate still attacks our carbonyl carbon. The only reason they get a special new name is because apparently, probably Mr. Claisen happened to test this reaction after the aldol condensation or the aldol reactions were figured out and said, oh, it's an ester, so now it's magically my reaction. The chemistry is 100% equivalent. There is no, well, it's not completely 100% equivalent. So let's go through and take a look at some adjustments. We take a look at the upper right-hand corner where we've got our summary for it. Okay, our end result of the Claisen reaction looks like this guy, right? How is that different from our aldol? There's no alcohol. We end up with a ketone, okay? We end up with a ketone and an ester as opposed to an aldehyde and an alcohol, okay? Any ideas why? What happens when our nucleophile attacks our electrophile? What bond breaks? Pi bond. But then we've got 3 very electronegative elements attached to our carbon. Carbon gets pissed and takes some electrons back. Where does it take the electrons back from? But now we're back at an issue. What's that issue?
Too many bonds.
Too many bonds. So what bond do we break?
Something that leaves.
Why do you break it to the oxygen? Oxygen is more electronegative than either of our carbons. Okay. If we look at the possible, or the resulting product of this, we have R, well, I guess I should draw that. O carbonyl. There's our carbon, goes up to our carbonyl and carbon, and we end up with OR. What happened? I guess you can see it better on this, on your right screen. Where's the negative charge? In both cases. In the reactant, where's the negative charge? On the carbon. Where is it in the product? Oxygen. Which one can hold the negative charge better? Oxygen. That actually is a reasonable mechanism. Okay. You'll notice another big key difference in here is that when we did the aldol, we only reacted with a base, and it was one step. Okay, so there's a base that's being added. We do just one step. Oh, interesting. Our Claisen actually have 2 steps. So the chemistry is very, very similar, but we see some slightly different results that come out of this. So we've got to be a little bit more careful about what's happening. So let's take a closer look at some of these. Okay. So when we compare between our aldol and Claisen, okay, what we just looked at, we end up with, whoops, there should be an O in there. Okay. Our Claisen gives, we still maintain the original functional group of our ester, but then we end up with a ketone. In the case of the aldol, we still have our starting ketone functional group, but we also have that alcohol. So instead of forming an alcohol, we form a ketone. So we're seeing some slight variations within this. Then the reason being had to do with that initial attack, our tetrahedral intermediate on our carbonyl. Okay? We could kick off the OR as a semi-reasonable leaving group instead of kicking off our carbons. Okay? So that's one of our big differences between these, is we end up with 2 carbonyls as opposed to the carbonyl and the alcohol. Would we expect a condensation from this? Why not? There is absolutely still a hydrogen. In fact, I would argue that that hydrogen, whoops, I drew it on the wrong structure. We absolutely still have that hydrogen there. And I would argue on our Claisen that that is even more acidic. Why is it more acidic? Between 2 carbonyls. Why do we not see an elimination? See that condensation? What was our leaving group? Our leaving group in the case of the aldol condensation was an OH. Do we have a leaving group in the case of our Claisen? There is no leaving group. We still have that acidic hydrogen, but now there's absolutely no leaving group. Okay? So we won't see a condensation happen along with these. Okay, I don't know why I wrote Claisen condensation. Claisen reaction. Okay? So that was a pretty big typo. There we go. Quickly fixed. Okay? Next issue that we kind of addressed, okay, or alluded to earlier, is we said it requires 2 steps. And we also said that our Claisen had a much more acidic hydrogen, okay, than in our aldol. Not only is it more acidic than in our aldol, it's more acidic than our starting material. Okay? Which means if we go through and add the base to our ester, what's going to happen? Yes, we can get the Claisen, but as soon as we form our Claisen product, what happens? The base comes along, removes our hydrogen, and we end up with our enolate. Okay? We don't want that to be charged, so what do we have to do? We have to follow it up with an acid addition to go through and actually fully protonate. Okay? That last step is incredibly easy to miss. I will still consistently miss that when working with these. Realize that when you go through and do the Claisen, you must do that extra acidification step because you have an extra acid-base step as well that will happen on its own. You have to add that extra step of putting in that hydrogen to reacidify and get you to your final product. Okay? And have we seen this chemistry already? We already talked about why that position is more acidic. Remember, those are supposed to be oxygens, ROR. We talked about the diketone feature, making it more acidic. We talked about that way back at the beginning of this chapter, looking at our enolates. Okay? So you have to be aware of these extra little tidbits as far as the chemistry goes. On a multiple choice test, do you think that's really going to be all that important? Probably not, because they're probably going to incorporate the acid as part of it. Okay? So it shows up as a big issue on sapling assignments. If they ask you to draw out a mechanism, you'll probably end early and be like, well, I've already got my product. What happens? Why do I have to fill in all these other boxes? You have to fill in all the boxes because your product is actually more acidic than your starting material. So if you're in basic conditions, you're removing that hydrogen. Then you have to add your acid to put the hydrogen back on. It seems very, very odd as a last step or to have to go through and do that, but that's what the chemistry is doing. You have to follow what the chemistry does. Okay? So kind of be aware of that when we're looking at our Claisens. Why do I keep calling it condensation? It's bugging me. So we do have some limitations within this. Never mind. I know why we're calling it a condensation. Anybody know why we're calling it a condensation? It's not the same type of condensation that we did before. With the aldols, we formed a carbon-carbon double bond. That was our condensation. Did we form another double bond in the Claisen reaction? Remember, when our nucleophile attacks, it attacks our electrophile, and we break the pi bond. What was the very next step? You remake the pi bond, and you kick out a leaving group. So it is still officially a condensation reaction, but what we're eliminating from our structure is an alcohol molecule. Okay? So be aware that's where the condensation phrase is coming from. Not that big of a deal, but I just happen to see it now. Okay? If you don't like remembering it as a condensation, then don't remember it as a condensation. Just remember you kick out that leaving group. Okay, your OR. So some issues with our condensations. Our starting ester has to have 2 alpha protons. Okay? So to get this reaction to really push along, if we look carefully at the arrows that I drew up here, which way does our equilibrium favor? Reactant. Which way does our equilibrium favor? still going back towards our reactant. Okay. It favors, we might get a little bit of intermediate because we're putting that negative charge on our oxygen, but it's not a whole lot.
I mean, the second one compared to the third one is favoring the
And when we look at the third step,
intermediate there.
what's happening with our third step? Now it actually favors our product. That's really the driving step of our Claisen reaction. Okay? Why does that help us out? What's incredibly stable about this species? The resonance stabilization that could go either direction. Without that resonance stabilization, we don't get a whole lot of our Claisen product. Okay, we really need that extra resonance stabilization to help push and force our product to form so we can get it in a much higher yield. Without that last step, we don't really get it to occur. So if we start with an ester that only has one alpha hydrogen, we can't do that last step or the third step of our Claisen reaction. And if we can't do that third step, then we can't actually get our product. We end up seeing the reverse reaction dominate, and we don't see product formation. So when you go through and do your Claisen condensations, make sure you get those 2 alpha hydrogens. You need to have them. Okay, at least those 2 alpha hydrogens. Okay? Next big issue, you'll notice what base are we using in this case? OR. With our aldols, we could have used hydroxide. We cannot use hydroxide in the case of our Claisen condensations. Why? What is hydrolysis referring to? This species can act as a base. It can also act as a nucleophile. Do we have an electrophile? What can happen? It can attack and kick out this leaving group, like we want to do at a later stage in this mechanism. If we used hydroxide, do we have an ester anymore? No, we'd have the carboxylic acid. So when we go through and run the Claisen reactions, the base used is that small, I'm not quite sure what to call it, is our OR group in our ester. Okay, it will be the exact same thing. Okay? Because otherwise we end up with a mess with our ester product because we'll get a mix of what it originally was as our ester and then what the other base was that we used. Okay? So it's going to be one of the small things to notice when you run through it. Okay? The last big thing that's different is we will always follow up our reaction with the addition of H+, as a step 2. Okay? So your Claisens have a couple extra things to watch out for that make them a little bit different from the aldol. I personally don't think it's different enough to call it a whole new reaction, but I'm not fancy or important.
So what are we saying about the OR groups? Like if you use methyl, if the OR is
So let me
methoxide, you
clean
have
that
to
up a
use
little bit.
methoxide base.
If, instead of this being an R group, I used, let's make it extra different, a propyl group, and I went through and used ethoxide, when we get to the product, what should the R group be? It could be prop or it could be eth. I'd end up getting a mixture of both. If I get a mixture of both, that means they're going to have different properties when I try and separate them, and I'm going to end up reducing the yield about where I actually wanted the chemistry to occur, which is about that alpha hydrogen. So if I have a prop R group, I need to make sure that the base I use has that same prop R group. So that way when it does the reaction with that ester, it doesn't change the ester functionality. It stays exactly the same. Okay? So that reaction will still be occurring, but it doesn't do anything productive. It doesn't do anything different from what's already there. Does that make sense? Okay. Other questions? So those are your basics of your Claisens. Just like we did with the aldols, you can do crossed Claisens. You get the exact same types of considerations. We want one of our esters to have enolizable hydrogens, the other one to not have enolizable hydrogens. We want to minimize sterics as much as we can as well. those things are going to help us propagate and actually get the product that we want. Okay? The other thing that we could go through and do is use an incredibly strong base like LDA. Why can we get away with using LDA and not our alkoxides? Remember our alkoxides, we said it had to be exactly the same, right? OR. Why am I allowed to use LDA and have it not be an issue?
Because I don't do propane, not react.
LDA is a base, non-reversible. It's not nucleophilic. Okay? Whereas if we use an alkoxide, those are nucleophilic. Why is LDA not nucleophilic? The steric hindrance. You have to go back to the structure of our LDA. Those isopropyl groups prevent it from really reacting as a nucleophile. So it exclusively acts as a base. We don't have to worry about that nucleophilic issue. Okay? So we can still get away with using that LDA or other bases as an option. Okay, other questions? We can also do intramolecular Claisens, just like we did with the aldols. Same general idea. Identify your nucleophile, identify your electrophile, and run the reaction. What size rings would we predict to occur? 5- and 6-membered rings, just like with the aldol. Okay? You might see this name pop up. Okay? Again, this chapter is full of names for some unknown reason to me. We're all ultimately doing the exact same chemistry. In this case, it can be referred to as a Dieckmann cyclization reaction because he was the first one to run the intramolecular Claisen condensation reaction. Okay? Do you want me to try and draw out the mechanism for that, or do you think you guys come up with that on your own from the aldol? We're letting that slide as our aldol. Okay? You should be able to go through and do that. If you've got questions, you can talk to me after class, and we can go through it step by step. Claisen condensations. Where should we go through and break these? All right, let's take a look at our first one. Where's our ester? We have an ester hanging out this direction, right? Okay. That ester remained unchanged, which means which bond was broken? Good, carbon-carbon. It's either this one or this one. Okay, if we break it through here, should be saying no. Our nucleophile would come in and attack, right? So this carbon would be our nucleophile and attack. What happens? Kicks out the leaving group, or our ester. So that was the wrong place to close off our circle. Okay. So what we're doing is now cleaving this bond, and we want to split that off into an ester. Oh, this is a really ugly looking structure. And massive. Lucky me. That's our bond that broke. We've got our alpha hydrogen, which we decided was here, which meant what had to be at our electrophilic position. What functional group did we need? We needed an ester. Okay, what ester do we put out there? What do you mean same one? Has to be the T-butyl. If it's not T-butyl, then we're going to get a mixture of esters coming out with the other end of it. Okay? Has to be exactly the same. So what type of Claisen did we do here? Intramolecular. Happened within the structure. Okay. Second reason why our intramoleculars are going to be more difficult to see. They are ugly, but more than likely when they're given to you as a reactant, are they all nicely folded up into the position where you can see the ring? No. Okay. They're drawn out nice and flat, so they look nice and pretty. And and don't allow you to really see where your bonds are breaking and making. Okay? Let's take a look at the other one. Should we take a look at the other one? Okay? Identify your ester. Which carbonyl, top or bottom, is part of the ester? Bottom. When we look at our Claisens, the one that stays in ester supplied what? The nucleophile or the electrophile? The nucleophile, which means it had the alpha hydrogen, has to be included in that. So the bond that we broke, okay, or the bond that we made actually was that one. We're looking at with something attached out there, and then we've got, drawn very softly, sorry, this guy. We've got all our carbons in there. This carbon was ultimately our enolizable hydrogen. It had to attack our electrophile. So it comes in and attacks, but we need to have something to kick out. What do we kick out? It's going to have to be our oxygen leaving group, and it needs to be an ethoxy. Okay, so it has to match that other ester. Okay. What type of condensate or Claisen did we do here? Crossed condensation, or a crossed Claisen reaction. Okay, because we are starting with two different esters. Okay. Questions about that? Okay.
So can I ask a quick question?
Yes.
What is a Michael reaction?
That's exactly what we'll be talking about now. We're running a little bit short on time, so I don't know exactly how far into it we'll get. We'll kind of just have to see and go from there and decide what material is going to show up on the exam or not. You will see probably very limited questions on your Michael, because I don't think I'm going to cover in the next 5 minutes all of it. Okay. The very last type of reaction that at least I've separated out from the textbook, so I think I went in a slightly different order than what the textbook had organized, is looking at chemistry happening at the beta position. Okay? What do we mean by the beta position? So if we go through and take a look at our aldol product, okay, from an aldol condensation, we have our carbonyl, and we go to our alpha and beta, and what we're talking about now is an alpha-beta unsaturated carbonyl, or alpha-beta unsaturated, yeah, we'll stick with carbonyl. By that unsaturation, we mean we have that double bond. Okay? How does that change things? Well, if we go through and look at resonance structures for that, we've got 3 of them drawn below. Which of those 3 resonance structures show an electrophile? The last 2. We're looking at our electrophile having a positive charge. We're looking at the carbonyl carbon. We've seen that chemistry before, but we're now also looking out at that beta carbon. That beta carbon can now act as an electrophile as well. That's ultimately what your Michael reactions are looking at. You're looking at the alpha beta, or sorry, your beta carbon acting as an electrophile. And there are certain conditions that are going to help facilitate that beta position reacting. Okay? For instance, if we react to this compound with a Grignard reagent, where would the Grignard reagent attack? What charge is our Grignard reagent? Negative. So let's just say we had CH3 minus. Where do you think it would attack? The electrophile. Which electrophile? Preferentially targets the carbonyl. Okay, why the carbonyl? This is arguably more positive. Why is it more positive than the other carbon?
The stronger negative pulling electrons.
What's the strong, and I don't quite like stronger negative.
You have a more electronegative.
Yeah, you have a more electronegative atom attached to it. You have that oxygen, making that carbonyl carbon slightly more positive. Our Grignard reagent is so ridiculously negative it is going to react with the most positive thing as swiftly and quickly as possible to neutralize that positive charge. So our Grignard is still going to seek out our carbonyl carbon. Okay? If I want that beta position to react, what do I have to do then? Okay, well, we just said we're not going to be able to make it more positive than our carbonyl carbon. We already have that oxygen there. That's not going to help us. And we said our Grignard is going to seek out the most positive. So instead of having something ridiculously negative, maybe we should have something that's a little bit less negative. Give it a little bit more time to kind of seek out individual reactions, okay? To seek out that beta position. So what ends up happening is we're going to use a slightly different nucleophile, okay? There's a couple ways that we can make these different nucleophiles. We can look at it as a copper compound. You're looking at Gilman reagents. Those will attack your beta positions. Okay? You'll hear different phrasing with this too. Your Grignards are 1,2 addition reactions. Why 1,2? What are the two groups that were added in the case of our Grignard reagent? One of them is nicely highlighted for you. You got the R. What else was added? The hydrogen. If oxygen is atom number 1, we added a hydrogen to position number 1, and position number 2, we added an R group. So we're looking at a 1,2 addition reaction. What happens when we look at our Gilman reagents? What were the things that were added? Okay, we've got our R group. Okay, and oh man, we have to go through a keto-enol tautomerization on this. We end up putting a hydrogen up there first. All right, let me draw what we generate before we get to that product. We generate this product first with our Gilman reagent. So we put on our R group and we put on our hydrogen. Those two groups were added at what positions? 1 and 4. So we have a 1,4 addition. Okay, why does it end up shifting to be the product that's actually drawn? What's the relationship between those two? I'm out of space. The relationship is that they are tautomers. Okay? So when we do our addition with the beta reaction, or sorry, our Gilman reagents, we get that beta position to react with our R nucleophile coming from our copper reagent. Okay? That generates one of our tautomers. That tautomer switches back to the more stable form, which is the ketone. Or sorry, the carbonyl. In this case, it's an aldehyde. Okay? So we get what's known as a 1,4 addition. Okay, so what we want is some kind of a balance between a Grignard and a Gilman reagent. The more negative or the more active our nucleophile, the more likely it's going to attack the carbonyl carbon. The less nucleophilic it is, we're going to see a little bit more of the beta position. Okay? And ultimately, it's not going to attack that carbonyl carbon because it's not quite as nucleophilic. We see a little bit more stabilization. And what we're looking at is an energetic difference. The pi bond on our carbonyl is a little bit more stable than starting with the double bond in our starting material, or sorry, in the Grignard reagent. Okay. So when we go through and look at the individual mechanisms, remember I said we ended up with that tautomer as an intermediate. So we have our nucleophile attack the beta position. We see that shifting around. We get that tautomer, or our enol, keto-enol tautomerization. We get our final product where it looks like we've actually put our hydrogen and nucleophile in different positions, but our 1,4 addition is ultimately coming from this guy first. Okay. The other name you'll see are your conjugate additions. Okay. Because this was ultimately an enolate chapter, we were looking at our alpha carbon acting as a nucleophile. We now want to kind of figure out where it would fall within this. Your Gilman reagents are kind of your least nucleophilic, your Grignards are the most, and enolate falls somewhere in between those. Okay? A standard enolate, okay, if we just take a single carbonyl, okay, just a single ketone, that species gives you a mix. Okay? It has some stabilization that the Grignard doesn't have. Okay? So it's a little bit less nucleophilic than the Grignard, but it's not quite as stable as a Gilman. Okay? Which means we end up with a mixture of both the 1,2 and the 1,4 addition reactions. Okay? So we get the enolate acting in both conditions. Okay? If we really only want the 1,4 addition, we need to further stabilize that enolate. How could we stabilize it? It needs something else to resonate with. If we compare those two carbonyl compounds, both of those are going to generate an enolate. Which of those enolates is more nucleophilic? Left or right? The left, because less resonance to go ahead and stabilize it. So if we really want the 1,4 addition, what we really need to start or use as a reactant is a doubly stabilized enolate. So we need those two carbonyls. That species gets a very special name, and since you asked for it, those are Gilman reagents. Or sorry, not Gilman, Michael reagents. We're running a Michael reaction. Okay? So we have what's known as the Michael donor reagent. Why is it the donor? It supplied the electrons, and we have our Michael acceptor. Okay. We are officially out of time. I think the rest of the material, if you let me scan through it real quickly. Oh, we did miss a couple things. So there's a list of common Michael donors and Michael acceptors. So your acceptors are that alpha beta unsaturated ketone. Your Michael donors are your doubly stabilized enolates, so those two carbonyls. Okay. Things that we have not covered, so I will not ask questions on the exam on the next sequence of material that we'll talk through real quickly. So Michael additions, you can expect one question on that. Probably won't ask any more than that. We did not talk about the Stork-enamine reaction. Okay. Ultimately, this one's kind of neat because you're combining stuff from chapter 20 to form the enamine, and then change that alpha-beta chemistry that we just talked about with our Michael reactions. All right? So all of that is still your enamine. There's another random one. And then the Robinson annulation. Okay? That one won't show up on the exam either, though that one you could officially probably do on your own, because really it's yet another name given to reactions that already had names. The Robinson annulation is a Michael addition followed by an aldol condensation. Okay? The rest of it, I'm pretty sure, is just review, synthetic strategy stuff. Okay? So for the exam, no Robinson, and then no Stork-enamine. Okay? And then very limited Michael questions. Sorry, I shouldn't be cracking my knuckles into the microphone. Okay. Any questions?
So the test is